Hi, everyone. Welcome to that Design Tips webinar number 2. My name is Marc-André Cailler, also known as Mac here at Vention. I'm an application engineer, and I will be your host for today's Design Tip session on how to choose your actuator and size your stepper motors. So I'm pretty sure you already had a project in the past where you either had to create a palletizer, lifting application, or a 3D printer, or even maybe a 3-axis scanner. And you were wondering, okay, so these are my dimension and everything, and how should I choose my actuators? What would be the thought process to get that sorted out? And then once I have my actuator, should I get a small motor, a medium, large? So today I'm going to try to help you out finding that. So we'll go through the steps from the actuator, the stepper motors, and then a little bonus. We'll see a bit on how the machine logic can be helpful to simulate all that. And after all this, we will have a Q&A session. So you can go ahead and ask your question under the Q&A tab of the webinar, so you can ask them in advance. And I'll pick a few one. And if I didn't answer your question during the webinar, we'll make sure to follow up with an email later today or tomorrow. And also you can feel free to comment on the chat if you have anything to say. Also, I just want to warn you, I'm working here in the manufacturing environment, so you might hear a few loud noise, and we're also startup, so there are dogs around, so don't be surprised if you hear a dog around. All right, so let's get started. So to better support you in that quest for actuators and stepper motors, I think it would be best to find sort of an example, a model that could be reproduced on your side. So even if you're trying to design a palletizer, the example that I want to share with you will be valid. We will look for a 3-axis scanner as it is getting more and more popular here. And yeah, we'll follow this example and make sure to repeat the same process for your application. So, all right, so let me share my screen on Vention webpage. There you go. All right. So here you are on Vention website. I'm sure most of you have already been on this website yet. And as you know, you have the 3D builder here. You can start the design from there. But we also have the public's designs that are here. So, so today, if we're trying to find a 3-axis scanner, we could go right ahead and click on public designs and search for scanner or scanning. So here we have a bunch of examples, but I think this one would be the best. So you can go onto the summary page and even scroll down to documentation if you want to download a 3D model for it or a PDF quote. But what we want to see is more in detail. So we'll open the 3D model with the Vention 3D builder. So for those of you who don't know, Vention has a free software, some sort of CAD. It's not exactly a CAD because what we have here is industrial, what I like to call Lego parts. So they are all preloaded, so already available for you. You can just pick them up from the powered browser on your left and put them in a design in the 3D space and just snap them together very easily to make your design cycle a lot faster. So our model is loaded. Let me get the laser pointer out so it's clear. There you go. So here we have a 3-axis scanning unit. You can go back to the summary page to find sort of the travels and the dimension. Seems like this one could fit our application. So here we have 3-axis, so a dual x-axis that we have here, right there. We have in y-axis, if we click on this face, there we go. So the y-axis is here. And we also have a z-axis going up and down to adjust the height of the scanner. All right, so you may wonder, okay, so why are they all ball screw here? And why are all the motor small motor? So those are very good questions, and you've came to the right place. So, alternatively, you could just take this design and say, oh, well, it fits what I want, and you're done. So you can find it all on the public designs. But yeah, no, if you're more curious and if you want to really see, okay, is that going to suit what I want to do with it? So here's what you have to do. First, like I said, you identify your axes, and what we're going to follow is you will need to write down some factors to see if this one can fit what you want to do. So let me present you the different factors. There we go. Okay, so here, to properly choose your actuator, speed is going to be very important. So you need to find out your maximum speed. It's not necessarily sort of the medium speed or what's the minimum speed, but the maximum speed is really what is going to limit or narrow down your choices. The load. So in our case, the load is going to be a scanner. So on the tip of our z-axis, we're going to install a scanner. So pretty light. The travel. So again, for a scanning application, it's going to be like, so what's the size of the part that we want to scan? That's going to determine how much travel we need. And the repeatability is basically how precise you need this automated system to be. So, and lastly, yeah, we don't need to, we need not to forget this one. So this is sort of the joker, like the factor that can really help you to narrow down between two good options. It's the application specific factor. So it could be either like the fit or the footprint, resolution. And by resolution, I mean there will be a difference between the timing belt and the ball screw. They have different speed ratio. So for the same motor, they will move at different length. And this is going to change your resolution. And as we will see later, we have also options to micro step the stepper motors or use a gearbox to change that resolution depending on your choices. So here it could be all sorts of factors that could help you like very specifically for what you want to do, help you narrow down your choices. All right, so for our example today, I prepared an example using a plate of a dimension of 1 by 1 by 10 and a hole pattern that would have 10,000 holes to be inspected, and they would be in some sort of shape like a grid. And this grid would be 5 millimeter square. So from one hole to the other, 5 millimeter, and same thing on the other axis, which would be X and Y. And we, most importantly, we want to we want to complete the inspection of this whole plate under 85 minutes. All right, so with all of those information on hand, we can move to the next slide, which is a flowchart. So here, I built this flowchart to help you find, again, like narrow down your choices. So we'll start with one of the axes. So going back to the design, if we look at this 3-axis design here, you could start most likely with the x-axis. Seems like my laser pointer is stuck here. Let me check if I can debug it. There you go. Aha. Okay, so if we start with the x-axis, we could find out basically everything that we need to move this whole carriage here. So it would make sense to start with this one, as the other ones are connected to it. So what will be important here is that the load on this axis is not going to be only the scanner, but everything that moves with this x-axis, so the y-axis and the z-axis at the same time. So the first thing that we want to do to know that load is going to be to actually find out the mass. So here with the Vention 3D Builder, a cool and very nice tool that we have is that the price, the assembly time, and the weight are updated live. So anytime you add a part or you remove a part, it's gonna make it change. So what I like to do is just to draw a rectangle, making sure that everything in here is selected. We can unselect the stuff that we know for sure it's not going to be part of it. And then you just Control and copy, Control C. Then move your cursor just a few meters away, and Control V to paste what you've just selected. And this is going to make the weight change. We'll make sure to do a nice cleanup, make sure that we have our formation that is accurate enough. We will include some safety factors, so it doesn't matter if you have a plastic cap that shouldn't be here, or maybe a small plate or a gusset. So just continuing my cleanup here. So the ball screw itself won't be, it will be rotated, but won't be actually moved, translated with the rest. And again, like I said, with the safety factor, we should be precise enough for what we want to do. Okay, so here I have pretty much all I need to move on this X carriage. And we see that we have a weight of 320 kilos. So the only thing that's left to do is take this carriage and delete it. So you can use backspace or delete when you're doing that. So we're going down to approximately 250. So it makes a difference of 70 kilos. But as you can see, we don't have our scanner yet. So you can use whichever scanner suits your application best. So we will take a guess that this scanner will be weighing about 10 kilos. So adding to this 70 kilos, we have a total of 80. So 80 kilos, perfect. We have our mass. We can go back to this flowchart that will be actually added to the tech docs, which will be back very soon. So let's go back to this flowchart first. All right. So let me get my laser pointer back. Seems like it gets stuck once in a while. Okay. Well, I hope that you can see my cursor, as it seems like it's frozen there. All right, so starting from the top. So our application, we know that it needs to be under a full cycle time of 85 minutes, but at the same time for 10,000 holes. So that doesn't tell us the speed itself, but we know that from one hole to the other, it's only 5 millimeters. So it's going to entail that the maximum speed won't be very high. The acceleration might be high, but not the maximum speed. So it's most likely going to be under 500 millimeter per second. Here, travel. So as you might have seen, our travel is less than 1,300 millimeters. Pardon. And we're getting to orientation. Our x-axis is horizontal. So we'll follow this path. And boom, we have timing belt or ball screw. So we have a choice here. And then comes in the last factor that I was talking about, fit, resolution, and maybe also if you have one type of actuator, maybe you want to sort of make them all the same so that it's easier to configure and to install. So in this case, since the ball screw has a natural resolution, naturally higher resolution as it moves in shorter distance for one turn of the motor, we'll go with the ball screw, and at the same time to do sort of enclosed, nicely enclosed design, the ball screw are doing a great job. But as you can see in this flowchart, there is a rack and pinion, which we recently added to our platform. It's not yet in the 3D builder, but it's coming very soon. And as you probably noticed, we have a bunch of parts and new features that just get added every week, every month. So make sure to go back to the Vention webpage frequently so that you get those updates. We tend to write nice blog posts to explain to you what are new features and tutorials and everything. And maybe another webinar to explain maybe more in detail the machine logic, which we will cover briefly. So here we got our first axis done. We would then repeat the same process to find out what we would use for the Y and Z axis. But like I said, it might be better to choose the same if you can, if you have this option in the flowchart, and if it makes sense to use the same kind, just for ease of installation and maintenance and everything. So next, now that we chose ball screw for this dual axis, so one ball screw on each side, we need to find out is the small motor here strong enough to actually perform this scan at the cycle time we need. So if we go back here to our presentation there. So there we go. So that's our methodology that we're going to use to find out if the small stepper motor is strong enough. So we will need to find the torque required for this application that we have. We'll need to find what's the maximum speed of rotation. We're talking, it's most likely under 500 millimeter of translation, but how does that actually translate into rotation on the stepper motor? And finally, once we have this information, we will go into the data sheets and find out if everything stays under the curve. So we'll get to this point very soon. So the first thing that we want to do is calculate how much time that is going to be spent on like one whole cycle. So we have this complete cycle time of inspecting the 10,000 hole, but what about one hole? So going from the previous hole to the next hole. So here we just need to take this target, the cycle time we're aiming for the whole thing. 85 minutes makes 5,100 seconds. And then we're going to subtract 100 seconds. Here's why. So let me go back to the design. Here, you might have noticed that we have our best friend and best colleague, Gary. So Gary here is our technician. He also helps with proportioning, as you might have noticed. Gives us a sense of how big this is or not. And Gary will be the guy that loads and unloads those plates to be inspected. So we need to allow him some time to place the plates against the datums and also prepare them before he hits start on that machine motion pendant to start the scan. So everybody loves Gary. We want him to stay healthy for a long time. So we want to make sure that he has a decent amount of time to actually make that change. So we're going to give him about a minute and a half to do all of that. So going back to the slide here. So a minute and a half is 90 seconds. We're going to give him in 10 extra 10 because such a nice guy. And so that comes down to 5,000 seconds. So 5,000 seconds divided by 10,000 whole, it's going to be 0.5 seconds for each smaller cycle. So here, down here, we have the velocity on the sort of y-axis, and on the x-axis, we have the time. Typically, your stepper motor will have this trapezoidal curve. And we know that from the first hole to the second, and then we also need to take into account some scanning time. So here, we're going to have an acceleration. We're going to reach our sort of cruising speed that's going to be super short, and deceleration. And then we need to allow the time that the scanner needs to do its job. So here I started by giving a 0.3 second time for the scanning to do its job. It's arbitrary. If you have your scanner model, it's best to find out what that is first. So that leaves us 0.2 seconds, so 200 millisecond for the movement of your scanner from point A to point B. And what we will do is make it more simple, because if we have this cruising speed and acceleration, deceleration, it might be hard to find out how much time is going to be spent accelerating, decelerating. So we'll make your life easier. Why don't we make it accelerate up to the half of it and decelerate to the other half. So that gives us 100 millisecond to accelerate from here to there. So it's going to be half the distance to carry that job. And so it gives us more information. So knowing that, we know that the stepper motor must be strong enough to have this acceleration here. So the acceleration is going to be represented by the angle of that line here. We're going to use some kinetics equations. Well, one is kinetics for constant acceleration. That's also another hypothesis that we're using. So we know here our final position, which is going to be half of the distance, so 2.5 millimeter. And we need to find the acceleration. We have the time. The time is actually going to be would be half of 100 millisecond, so that would be 50 millisecond. And yeah, so 200, yeah, there you go, 50 millisecond. And Then we're going to need a second equation because we have to find the force to convert it into the torque. Then knowing if we have if our small motor is strong enough. To find that force, we need the mass that we previously found, 80 kilos, that we're going to divide in two since we're going to analyze just half of it to know like each of the motor how big they need to be, and we have the acceleration again. So two values unknown, acceleration and force, and two equations. So we can solve that out. As you can see here, we have 2 meters per second square and 80 Newton. So from when you have found those two parameters, you can go back to the data sheets. So let me show you where it is. So go back to the Vention main page, and here under those tabs you will find resources and then tech docs, and you will land here. And under tech docs, open the hardware section and find your actuator datasheet. First, before going to ball screw linear actuator, I just want to show you that there's also complementary information about what we're talking today on selecting the right linear axis actuator. So that it's plenty of information that might help you on top of what I'm explaining here. And most importantly, you have here a nice graph that we drawn for you with the ball screw in dark blue and the timing belt in light blue. So as you can see, timing belt can reach a lot faster, higher speeds, and the ball screw can have a lot more force to move different parts. So going back up, we'll go to ball screw linear datasheet. And from here, I just need to scroll down to the technical specification. So here under technical specification, you have the different lengths available. You have the speed ratio, which we'll use under the next step. And we have the linear force to torque ratio, which is 565.5. So this is what we needed today. Going back to the slide. There you go. So force to torque ratio, 565.5 Newton per Newton meter. And we have 80 newtons from what we calculated here, thanks to Newton's second law, and the torque ratio. And we're going to add in a efficiency percentage. From the torque output of the stepper motor, you will find that there's a mechanical loss from that output all the way to the gantry that you're trying to move. So this is characterized to be about 10% loss. So we're going to factor that in, making sure that what we're giving to that actuator in output is going to be sufficient to move everything. So 0.16 Newton meter, not a lot, right? And from there, we got our torque. Perfect. All we need to find now is the max speed. The max speed of rotation for the stepper motor is going to be found with what we got on the data sheet, the speed ratio. So 10 millimeter per turn, it's directly related to the pitch of this ball screw. So 10 millimeter per turn. And we got back our whole 5 millimeter spacing between those two holes. And we need to achieve that under under 0.1 second with that safety factor of 2. So just to give you a bit more information on the safety factor, it's basically, since we're here for this application, our main goal is to scan this plate under 85 minutes. We want to make sure to reach that, right? That's our primary goal. It's to scan the holes and do it in a productive way, in a conducive way to you. So we're adding this safety factor to the time that we're using, so that we have something that for sure is able to do your scanning, your total cycle time in 85 minutes. So there you go. So that gives us 50 millimeter per second of movement from one hole to the other. And then we're going to convert that into RPM. So using the ratio and also there's 60 seconds per minute. So that gives us 300 RPM. So with those two parameters, we can go to the next step. And here we have 0.16 Newton meter and 300 RPM. So we're going back to the data sheets. Here, if you scroll down, you will find that for this ball screw, we have already drafted those three curves that are related to the size of the stepper motor that we have here in stock, available to ship next day. So here we have the 65 millimeter in green, the smaller stepper motor. We have the medium in light blue, and the 156 millimeter in dark blue, so which is the larger of those three. As you can see, we have it in force, so we can use either our 80 Newton here, or if you go directly to any of those stepper motors data sheet itself, you will find the torque to speed curve. So that's why we were finding them both. So here, 80 Newton, so we're pretty low there, and we don't have the speed in RPM. We have it in millimeter per second for this one. So we had 50. So 80 newtons, 50 were way under this curve, this line green curve. So let me show you how it looks under the data sheet for the motors. So right now the data sheet for the motors are in the parts library. You just need to type in stepper or motor, and we'll take a look at this small motor and go down to data sheet, download it, you can open it here. And if you scroll down, you'll have the torque curve that I was referring to. So you have it here either for a 3 amp output or half of it. So the difference between those two is that for our axis here, going back to the design, so for our x-axis, we're going to use one output to serve those two motors. So looking at the machine motion, we have 3 outputs. One is going to go to each axis, and means that the x-axis is going to be split in 2. So going back here, it means that we need to use this 1.5 amp curve. We can double check it. So we have to the point, if I can correct, yeah, 0.16 Newton meter and 300 RPM. So we're still way under those curves. And now the 3 curves that you see, they're not related to the different type of motors. They are actually related to microstepping. So as I was referring to earlier during this webinar, you can microstep your motor. So if you're looking to have a higher resolution, but that will affect the maximum speed for your axis, and also the maximum torque that you can use while you're microstepping. So make sure to have this in mind, but that gives you a different combination of axis and motors. If you really need a certain type of axis to do what you want to do. So you have option A to microstep, and you have another option that would be to use our 5-to-1 gearbox. So it's going to reduce the speed, increase the torque, and yeah, so that would be different options that you have. So good. Now that you have found that the small stepper motor is going to be sufficient for both of those x-axis, you can repeat the process again for the y-axis and the z-axis. And so now you have your design, all the parts are in there. So that's great. And you need to make sure that you've added also all the automation components, such as the sensors and the machine motion, for example. And once you have that, the machine motion and the sensors, you can open the machine logic button right here, and you will be able to program a sequence and visualize it in the 3D builder. So you will be able to actually see what you want to deploy, and when it's done, when it's at your liking, you can actually deploy it to the machine motion. So you just need to find your unit and make sure it's connected to your network or to your computer and deploy it directly. So here, all you need to do is click on configuration and configure your axis. So even if we have a dual axis here, you can still use just one actuator to make the X carriage move. And also just a good trick to know, as you can see, the sensors have a numbered name, but there's a small trick that can help you out. If you open that tree view and click on that sensor, it's going to auto scroll to it. And then you can right click, rename the sensor to be like X home sensor. So this way it's going to be a lot easier for you to go back to the machine logic and actually see that it's the X home. So here, I'm just going to switch it with the other one, or actually rename it so that we're sure that we have the good thing. This one here in the tree builder. And this one's going to be the end stop. So I'm going to switch them up. So X end stop. There you go. And there you go. So I'm just going to switch them here. And X stop. And you can do the same thing for the y-axis and the z-axis. Perfect. So actually, yeah, this might affect my my sequence here. So I'm just going to make sure to reload that. So while I load it, I just want to tell you that we're continuously improving the system that we have here. So very soon we're aiming to implement the total cycle time for the program that you're designing. So I just want to make sure that all my program stays intact to demonstrate it to you. So here, with that application, we will be able to show you. So, okay, so with all of the movement that you've programmed, here's the cycle time that it should give you. So it's going to confirm what you calculated here. So here with this application, I've created a master sequence that will start by homing the motors and moving them to a set position. As you might have noticed, the z-axis shouldn't move a lot for scanning holes. It's just going to be focused at the right height. So it's going to be set at first, and then later in the sequence, it's going to actually call for other sequences that and the reason is for why do we have so many sequences is that we can change the type of sequence to either just do it once or change it and to loop it for a few times, or maybe you wanted to move it forever. So having the ability to loop it for a count of times allows you to build those more complex sequence like this and be able to scan 10,000 holes. So let me just click play here. And as you can see, everything that is being used right now is going to be highlighted. So you can switch from one sequence to the other. and actually see what's in function. You also have a debug mode and everything. So here, my scanner is scanning one hole at a time, and I have set my my speeds initially in the first sequences, so according to what we calculated and everything. So that makes your programming a lot faster. As you can see, it's all drop-down menus. You don't need to know a new language of coding for a guy like me with a mechanical engineering background. It makes it so easy. I think like as soon as you pick up, okay, so what does this function do? And we have a lot of help for you to find out what everything does. So you need to go under resources and tutorials and tech docs to find the different help sheet that we created for that. And then you should be able to create either a simple app or more complex like this. So there you have it. The machine logic at the end of finding out our steppers, our actuators. So I'm gonna take a quick pause and look at the different questions if we had any today. So I don't see that any of you ask a question so far. So I'm just gonna, well, I wait to see if you have any. If you have any question right now, I'm just going to take a look at the chat as well. Maybe there's a question in there. I can also show you, meanwhile, like I said, we added this teach pendant that will allow you to actually see in real time the same menu that you have here on your desktop. So you can either program or control your application using either the machine motion pendant or your computer. So if you want to use your computer separately from your unit here, it's best to have a machine motion pendant that will say dedicated to your automated solution. Becomes more efficient for you. All right, so it seems like we have one here. So thank you, Chris. Chris is asking, how do you trigger a move from an input? Very good question, Chris. So here, do we stop there? So we have 4 different menus. Let me show you first where are all the information you need. I've briefly showed you, but I'm going to get directly to it. So under Tech Docs, you can go to Machine Logic, and here you have programming from the 3D Machine Builder. And you also have, so here's, you will see the 4 different types of sort of action that you have for your sequences. So you have activation signal and triggers. So all the nomenclature is here, and you have also using machine logic to program your machine to get more into details. So going back to your question, so how do you trigger a move from an input? So you will need to add, for example, in my master sequence, I would need to add a activate device here. So from a digital output, making sure that it's the right device and the right value to say activate or shut off. And from this point, you can add a move. So add the motor and change it from home to move absolute or move relative. But before that, so that if you just put it this way and change the position, let's say for 500, it's going to use the default values that we've included in the machine logic software. So it's going at the max speed and max acceleration. But before you actually put this motor step, you're going to want to set the speed and set the acceleration. So as you can see, I can create them afterwards and then just drag them to move them at the right place. So acceleration or speed can be one in front of the other and one at the back of the other one, it's both of them will work. And if you type something too high and press enter, it's going to go back to the maximum values supported by our hardware. They're not just random values. It's the maximum that we can support. So same thing here. If I press enter, so I can even support this speed. Going too fast, so we can go up to 10,000 millimeter per second. So there you have it. You can set the speed, set the acceleration, and move your motor after the output was activated. There you go. And after also, if you after this movement, if you want to call or execute another sequence, so the difference between the two is going to be that call will make the other sequence be activated in parallel, as the execute will sort of put it one after the other. So if you execute the next sequence here, as soon as we get to this step, it's going to fully execute this one before you do something else. There you go. All right, so I'm just going to wait a bit to see if anybody else would have a question. Thank you very much, Chris, for your question. And maybe meanwhile, I can give you a bit more information on the other loops that I created. So if I go back, I can remove all the things that I have here, just to show a bit more on how did I create this one more particularly. So if you always need to home all of your axes first, so that you start from a repeatable point. And then you can add wait time if you need. If not, you can skip them. I made my z-axis move by 300 millimeter just to set it at the focal point. Then wait for 50 milliseconds, set my acceleration and speed, and then execute the B loop. So B loop here is it's going to be actually used 50 times. The reason is that we're going to cover two rows of hold using this loop. So 100 divided by 2, 50. And in this B loop, as you can see, I'm waiting in between different moves, and I will execute my C sequence, which is 100 times X. So I'm going to move in the X axis 100 times to cover the 100 holes. And then at the end of this movement, I want to move by one row up in the Y axis. Pardon. So if we can take a look at this one, so X plus, Y plus. So here I also created sort of subsequences. Again, it's to control the number of times that it's actually looped. So I want to move my X here, so execute the X movement and then execute the Y. And as you can see here, the X plus movement will be at a count of 100, and the Y will be a type of sequence, which means loop one. It's going to do one, but if you only have one, it's not a loop, right? All right, so going back here, so it executes both movement, and here the X plus is really simple, is moved by 5 millimeter. Again, going back to this spacing that I had, and same will go for the Y-axis since we have a square grid. So there you have it. It really calls one another, and with the right count of loops here, it will make a sort of a zigzag pattern, making one row at a time, going up for 100 times in each direction, making covering the whole spectrum of holes, which was 10,000. So great. It seems like I don't have any other questions, so it's all I had prepared for you today. As I said, we will include the flowchart to the data sheets very soon. So this way you will be able to get started onto choosing your automated components for your design here with Vention. So thank you for joining me today. I really appreciate it, and I hope you appreciate it too. And until next time, happy designing.